stretches. Once you turn it off, it goes back to the left. And this is off, on, off, on, off, on, off, on. And we can show it's doing that here in these three videos. And it's black here because we put carbon grease on top and bottom surface so that the positive and negative charges are spread evenly. Now, first time I discovered this or found out about this phenomena of this dielectric elastomer phenomena, that it does this, it reminded me immediately of a muscle, right? Can this be an artificial muscle? And it's interesting from this phenomena, how do you use it to create, for example, an inchworm locomotion as shown here, or here, this is just basic up and down. And because you put electrical field across it, it generates mechanical motion. If you give mechanical motion, it also generates electricity. So this has high potential for being an energy harvesting device. Maybe indeed, from this basic phenomena of putting electric field, it stretches, turn off the field, it stretches back to its original shape. Maybe that basic phenomena can also be used as an energy harvesting device. Maybe put under our shoes as we're walking, maybe who knows, one day it will charge our phones. So these are very primitive forms of intelligent mechanics that we can use to create perhaps a new generation robots that have a better body. Now let's go further on the intelligence, a better mind. Intelligence is quite interesting because it has four components. First is sensing to understand the environment. Number two, planning what to do after you understand the environment. And third, executing what your plan, right? How do I do it? This is execution and control. And the fourth is continuously learning from experience. So we continuously do this, right? Now, this can be this loop, inner loop at 1, 2, or 3. This can happen simultaneously at a very fast rate. In low-level control, we can call that reflex action. In a similar way, if I'm a robot, if I touch my hand on a hot object, I quickly remove my hand away from the heat, right? I don't think I do some conscious planning and decision-making, but maybe it's inbuilt into my nervous system. I don't know, right? But then this is happening certainly at the reflex action level using internal sensors, but I can also move my body using my eyes, or drive a car, for example, using my eyes, and certainly that is happening at a slower rate, right? And these are different levels of intelligence, lowest level, middle level, higher level, and highest level, all happening every day, doing these four things. As these four things happens all the time, we continuously improve in the performance. So how can we have the robot have this in the robot's brain or mind with a better body? Two basic approaches to this, to intelligence or understanding the world. The first is the model-driven approach, where you have a physical phenomena that you try to model, and these are the inputs and outputs. You create a mathematical model to describe the relationship between input and output, and based on this relationship, you can control the world based on this understanding, right? But you can see how difficult it is. For example, the output is to walk so that you go from A to B. The input is the muscle forces in your legs and feet. How do you create a mathematical model for that? It's very hard. But we know how to do that because humans are walking, but we learn from experience. So this is the other approach, the data-driven approach, where we learn from experience. Somehow trial and error, like how a young toddler learns how to walk. Which to use, which is better? This is a constant debate. I think the answer is both are good. If we have models, why don't we use them? And we use the data-driven approaches to improve the models to make it accurate. Because we know data-driven approaches are never 100% accurate, but they can reduce the error. So the errors produced by inaccurate models can be improved through data modeling approaches. Although data-driven approaches doesn't need any scientific or mathematical model based on science, it has been demonstrated through some form of end-to-end learning to be able to do that. But if we have physical and scientific models, why not and use it? And that can be used, we can take advantage of that. So I'll give you examples how we do this for self-driving cars. Why I work on self-driving cars, because transportation affects everybody. And we've seen it in COVID situation. Even the COVID, there's no transportation, but there is still transportation of goods. In the e-commerce and logistics, it has improved, and you still need vehicles to move goods around, whether by air, by land, or by sea. So these are some of vehicles that we have started working on in 2010. And it has also these four things, right? Sensing is how to use the sensors so the vehicle knows where it is all the time without relying on GPS. How do you know that's a road? How do you know that's a sidewalk? And how to plan the steering, acceleration, and brake, executing the plan and continuously learning. Similar to how I learned how to drive when I grew up in the Philippines. It's fun growing up in the Philippines because I learned to drive by watching my driver bring me to school every day. And one fine day, I said, it looks like fun. Can I just take the steering wheel? And I did. After 2 accidents, I think I became a good driver. So the ultimate machine and tool is really the robot, right? And we are talking about mobility is an important capability, manipulation, right? My ultimate dream is really a mobile robot such as here on the lower left. And we can have a self-driving vehicle as the base, but can you imagine if that self-driving vehicle also has an arm and it can pick up garbage, it can clean tables, it can clean the road as it's doing it. So that is mobile manipulation. And this mobile manipulator is the ultimate tool. As the name implies, tool means it cannot operate by itself, but it's used by a human being. And the human with the robot, we work inside the society, so we don't do it alone. And this will really be revolutionized and put us all in startup mode. How can you use this to improve how we do things, to create new products and systems to make our life better? Right? And the rest, perception and intelligence, is very important together with a better body. And the focus is not factory automation, although that is very useful too, but we can do that if we can do it in our home, entertainment, leisure. I call this the 5 Ds of robotics: dangerous tasks, demanding tasks, demeaning, degrading. And the fifth one, most recently, I work on are driving vehicles, because these are tasks that are very boring and potentially a machine can do better than a human being. And safety is one of the motivating factors for working on autonomous vehicles. So to summarize, we need a better body, something like Baymax. Soft robotics is very interesting with a different kind of actuators. most robots today use motors, right? But human beings, our arms, biological beings, we don't have motors in our joints, and we use muscles, right? And our skin has very good tactile sensing. Our links are soft. We have haptics. We need a better brain, combining not only a neural network like our brain, combining also traditional flowchart-like intelligence. This is a combination of model-driven and data-driven approach to create a better brain and better body to work with us as the ultimate tool in what we all call as human-centered robotics. So it's exciting times now. We have many sensors available now, many better brains available on the internet that allows us to do data-driven. So even our young ones can quickly build something like this in sort of a democratization of robotics science and technology. And we certainly should facilitate that further. So thank you very much. I hope you enjoyed the video as much as I did in sharing this with you. Stay safe and healthy. Hopefully next year or maybe before that, we can see each other in person in a future robotics conference.